Now we will start with the second lecture in the BS Electrodynamics lecture series, and our second lecture is on the four natural forces. So this is the second lecture, and we will discuss the four kinds of forces. So these are the four natural forces, four kinds of forces. Now inside this one, we know that when there is a force, there will be motion, there will be acceleration. So the very first force that we will discuss is the strong force, which we also call the nuclear force. So this is the strong force. The second one is the electromagnetic force. The electromagnetic force. And the third one is the weak force. While the fourth one is the gravitational force. There is another addition, a recent addition to this list, and we will discuss that thing briefly, although it is not mentioned in your book, the DJ Griffiths Electrodynamics, but let me include this one in order to discuss this one a little bit. And this is the fifth one, whose nature is not one of these, and this is the Higgs interaction. Now, if this list is that small or that compact, like just four kinds of forces, then what about the other forces that we know in nature? For example, we are having the force of friction. With this force, we are able to move on a surface. If friction is not there, we will not be able to move on a surface. And the normal force which keep us falling, or which keep us falling through the floor, or if we place something, let's say, on a table, and this normal force keeps it falling to the floor. The normal force, then we are having a chemical force. Now, chemical force is the one which binds the atoms or the molecules together. So this force, what's the nature of this force? And similarly, when two billiard balls are colliding and their force or the impact between them, that kind of force, and so on. So in order to see the basic nature of all these kind of forces, so they are basically all electromagnetic in nature. If it's a friction force or it's a chemical force, a normal force, they are all electromagnetic forces, and we are basically living in an electromagnetic world, if it is not that exaggeration. So we will discuss these forces. We know about a strong force. Strong force is also called a nuclear force, and it is the force which holds the protons and neutrons together. Protons and neutrons together, and we call the protons and neutrons with a combined name is nucleons. The reason for calling them is nucleons is that inside a nucleus we cannot recognize which one is proton and which one is neutron, because they are interchanging in each other. So that's why we give them a common name is nucleon. The range this is the strongest force, and the range of this force is very short, and that's why we don't feel it. So if, for example, I consider the gravitational force is 1, then the order, it is greater than this one. The gravitational force is 10 raised to the power 38, and this is a very short range force which acts only in 1 femtometer, which is equal to 10 power minus 15 meter. So it's a very short range force. We are having the 1 femtometer is the size of the nucleus. So when it is more than the size of the nucleus, then this force is no more there, and the particles are being, or the nucleons are being separated from each other. So that's why it is called a very short range force. Then we are having some mediating particles for such forces, and the mediating particle which is for the strong force, we call it a gluon. Gluon, like it glues the particle together. So it is the mediating particle of the strong force or the nuclear force. Then another very fundamental force that we usually encounter is the electromagnetic force, the force which is the result of electric and magnetic field, the force which is due to the charge on a body, and when the charge is in motion, we call that current, and it generates magnetic field, and then it is the electromagnetic force. The range compared to this one, this force is 100 times smaller than that one, so its range is 10 to the power, its power is 10 to the power 36 compared to this one. And as we know that electromagnetic force is a long-range force and its range is infinite. And the particles which are considered as the mediating particles for the electromagnetic force are photons. They are photons. Now if we look to the two forces, then this force is a very short range force, and that's why we don't feel it. But we do feel the electromagnetic force. We encounter it a lot due to the reason that its range is infinite, and it is also a very strong force, although 100 times less than this one, but it is yet a very strong force compared to the gravitational force or the weak interaction. Is I know the phenomenon of radioactivity. Now I can see that the difference between these two forces is 100 times. So if I am just inside a nucleus, I am adding up the protons. Then these protons are actually repelling each other, and their repulsive force is increasing as I increase the number of protons, but yet the nucleus is stable due to the reason that there is another force, which is the nuclear force, which is 100 times stronger than this one. It holds the protons together inside a nucleus. But if I go on increasing the number of protons, then as it goes closer to 100, then we can see that radioactivity starts, the destabilization or the instability of the nucleus starts, because now the nuclear force and the electromagnetic force are becoming comparable, and that's why the nucleus will be no more stable. Another reason for this one, that when a proton means the size of, by increasing the number of protons, the size of the nucleus will be increasing, and this proton on one edge and this proton on the other edge will have comparatively less nuclear force and compared to the electromagnetic force. And that's the reason that when we go beyond 80 in atomic number, then the instability in a nucleus start in radioactive elements comes in action, and when we go closer to 100, then almost up to 100, 110 or elements, the stable element stops, and that's the reason that we are not having the atomic number much greater than 100. So these are the two very fundamental forces which play their role in the atomic, in the nucleus of a material. Then we are having the weak interactions, and weak interactions are the forces that are involved in the radioactivity or the radioactive decay, the radioactive decay. These forces are smaller than the electromagnetic forces, and if I compared them to the strength of them, so they are approximately 10 to the power 25 in this range, and their range is even much smaller than the nuclear force. It is approximately 10 power minus 18 meter, and 10 power minus 18 meter means 1 watt meter. It is this almost the size of an electron. So this is a very short range force, and we are having this force in the bosons like the W and Z bosons. And comparatively, if we compare these three forces, then their nature is almost the same compared to the gravitational force, because the gravitational force is a completely different force. So the nature of these are almost the same, while this one is completely different. So this will we are having another thing in this one, that these two forces have already been combined. The electromagnetic force and the weak force, they have been combined as electroweak force. They were combined by the Abdus Salam, Glacier and Weinberg. So this means their nature is the same, and that's why for this discovery, Abdus Salam and Glacier and Weinberg, they were awarded a Nobel Prize in 1979 on this unification. This was not the very first unification in the history of electrodynamics. We will discuss the unification from the very start just after a while, but this was the natural forces were then reduced to three forces by combining the electromagnetic force and the weak force. And the last one is the gravitational force. Now gravitational force we know from the Galilei and from the Newton equations that this is the force which is related to mass. Like it is a force between two masses, and this force is very small force. Like we consider in this order this equal to 1, then it is 10 power 25, then it is 10 power 36 and 10 power 38. The particles which are responsible for the mediation of this force, we call them gravitons. They are gravitons, and the range of this force is also infinite. Now this is such a small force that we cannot detect or feel this force for ordinary masses. This force is in a measurable size for when the masses are very huge, like for example the moon, the earth, or the sun, and so on. So for this force to be felt, the masses are to be huge. Now we know this fact as well, that when Einstein explained this force, he said that gravitational force is has nothing to do anything with the mass. It is not mass dependent, but it is actually a geometrical property. The gravity or the gravitational force is not an intrinsic property, but a geometrical property. It is based on the geometry, and this is based on the space-time curvature. Like, it has nothing to do with the mass, but it is a geometrical property. One body is attracting another body, then it is a space-time fabric, and when you put, this has no curvature in it, and you put mass in it, so it will produce a dip in it, and that curvature is actually responsible for this force. Like, it's purely a geometrical property and has nothing to do with mass. And the last one in this series of forces, we are having the Higgs interaction, we are having the Higgs boson, the Higgs field. So this is another recent entry into this list of forces. Like, the researchers are behind the fact that what things are responsible for giving mass to a body, and for that the Higgs field came in, and the Higgs field, like the Higgs particle, the Higgs bosons, Higgs particles, then they are responsible for giving mass to a body. However, all the aspects of this thing are not very clear, not very complete, and research is still going on this thing. Then we are having, in addition to this one, into these forces, let me further discuss that the electromagnetic forces or the electromagnetic field, they are the most worked out forces, and a very comprehensive theory exists for these electromagnetic forces. If I come to the gravitational force, then inside a gravitational force, I know that gravitons are there and it is force of gravity, but I don't have any quantum picture, like quantum picture of gravity doesn't exist yet, and that's why this force needs further understanding to know the nature of this force. Like Newton, Galileo and Newton portrayed it in one way, Einstein portrayed it in another way. It's a geometrical property of a mass, and here when we want to understand the very basic of something, then we should know about its quantum nature. So the quantum nature of gravity is not yet clear, and this needs further research. So we will go to the electromagnetic force, which is very clear, and we have a comprehensive theories for this one. Let's see, let me give you an example that if we consider, if we want to compare the electromagnetic force with the gravitational force, we know that it is 1 to 10 power 36. So if I consider hydrogen atom, then inside hydrogen atom, I know that the electron and the proton inside the nucleus, they are combined to each other, and the electron is going around the hydrogen atom, and this binding force is the electromagnetic force. Now, in order to compare the nature of electromagnetic force and the gravitational force, If I consider hydrogen atom, then a proton and the electron are bound to each other with electromagnetic force. So if I consider the electromagnetic force in comparison to the gravitational force, then the electromagnetic force is 1042 times greater than the gravitational force. Like if I consider the electrons, the electron and proton are bound to the gravitational force, and if they are bound to the electromagnetic force, then the ratio of the two forces comes out to be 10 raised to the power 42. Now if I say that this binding is due to the gravitational force, then the sizes of these will have to increase. And how much? Then the hydrogen atom will be more than, or should be more than, the size of the known universe. Like the gravitational force is such a small force that we need to increase the masses to observe this one. So if we want to increase, like we say that in a hydrogen atom the force is gravitational, which is binding the proton and electron together, then the proton and the electrons will have to be enlarged such that it is more than the size of the universe will be just one hydrogen atom. And that gives us a comparison between the two forces.